Hi, Michael Wolf, PGI Compiler Engineer. Today we're going to be talking about taking your OpenACC program and running them on both a multi-core and on a GPU. Today you can take your OpenACC program and compile it and run it on a multi-core with the -TA equals multi-core option. That's been available for a little while. When you use the multi-core output, or the multi-core option, the compiler essentially ignores the data directives and will generate parallel code or threaded code for your OpenACC parallel constructs. When you say TA equals Tesla, then it interprets the parallelism constructs to generate code for a GPU and the data constructs to move the data between the host memory and the GPU memory. Here we have two identical systems, each with a dual socket Haswell. Each socket has 16 cores, so for 32 cores total, and 64 threads with Intel hyperthreading. Each is connected to 2 Pascal GPUs, although we'll only be using one GPU today. I have two windows open. We're going to be looking at the SpecExcel OpenACC SP benchmark. I'm going to build this benchmark two different ways. The first way, at top, I'm going to build this with -TA equals multi-core. And in the bottom, in a different directory, I'm going to build the same benchmark for -T equals Tesla. CC60, because I'm running out of Pascal. And the difference in the informational messages will tell you, for instance, in this case it says here I'm generating multi-core code. And down here I'm generating Tesla code. So it's immediately obvious which target you're running on them. Now I'm going to run the ref dataset in each window. So in the upper window, it's running the ref dataset on the multi-core. In the bottom window, it's running the ref dataset, the reference dataset, on the Tesla. Now I'm not really here to compare the performance of the Tesla versus the multi-core, but I'm here to demonstrate a new feature that we have available that we'll see momentarily. So this is going to take about 2 minutes and we'll fast forward through this. So here both of them have finished. The Tesla code finished in 34 seconds. The multi-core finished in 1:45. Again, I'm not trying to compare the two times. Notice it used all 32 cores. It's pretty efficient then. But what if I wanted to only build one binary? Here I had to build different binaries to run on the multi-core from running on the GPU. What if, for instance, I'm running a big MPI application on a cluster where some of the nodes have a GPU and some of them do not? And I want to build one binary that will make use of that GPU on those nodes where it's available, and we'll use the very fast multi-core that's available on the nodes where it's not. So with PGI 17.7, we've enabled the option that allows you to do that. You can combine the TA equals Tesla with TA equals multi-core, either as a single flag or a combined flag. Now the question you might ask, and you should ask, is what's the overhead of doing that? How is that going to affect the performance? So let's check this out with the same experiment. So here I have my 2 times. We're going to try to remember these 2 times. In fact, I'm going to bring up another window. I'm going to build a single binary that will run either on the GPU or run on the CPU, and we'll compare the performance to when I had built the specific binary for a GPU or CPU. So the combined binary, I use the -T equals Tesla CC60, multi-core option. Same benchmark, SP benchmark, and here if you use these things scroll by, you can see the generating multi-core code and generating Tesla code for each one of those compute constructs. When I was generating code for multi-core, the data directives and the data clauses were essentially being ignored. When I'm generating a unified binary for both multi-core and Tesla, they can't be ignored. So you might well wonder, what's the overhead on the multi-core execution if I'm running this and I have to honor those data directives? Well, we'll see that it's not going to be very high at all. So now I have a binary that should work on both the GPU and on the CPU. In fact, not only does it work on CPU or GPU, it auto-detects. The default is, if there's a GPU available, it will run the GPU code. And if there's not, it will fall back to the CPU code. You can override that, as you'll see momentarily. So let me start by running the ref dataset, and as I mentioned, this is going to use the default behavior, which is to auto-detect determine that there is a GPU, a Pascal, and to use that GPU. So the behavior I expect is this should run at the same speed that the window just below it ran, 34 seconds. And there it is, pretty much exactly the same time. Now there's two ways you can override which device to run on. One of them is with an environment variable, which is easy because you don't need to change your program. You can also use API calls, or in the future there'll be OpenACC set directives to set which device is to set as the current device, and it will run all your compute kernels and data directives on the current device. In our case, we're going to use the environment variable, ACC device type, set that to host. I'm going to rerun, same binary, same directory, same machine, and running this on the Multicore. And if there's any justice in the world, this should take about the same time as the Multicore execution did. That's in the window hidden just below that. So as we saw, this takes about 2 minutes, so we'll fast forward through this. So this finished, took 1:47, just about the same time as the Multicore code itself did there. So this is a new option in PGI 17.7. It allows you to build a unified binary that would target either a GPU or the Multicore. We find this should be incredibly useful, particularly for people running across clusters that have different features in each node of the cluster. So I hope you can make use of this. Thanks for watching.